Okay, I thought I'd look at a problem like this where we've got a shaft and we want to analyze the stresses and what's going on if it's both experiencing a compressive force load here and some torsion as well. So we're trying to twist it and push it in, probably a bit like a drill bit or into a wall or a screwdriver, something like that. So let's start off with my numbers. I will have D, set that to be 50 millimeters. Set the force being pushed in at 220 kilonewtons and the torque at 650 Newton meters, and we'll have a factor of safety as well of 2. So what sort of things could we be of interest to analyze? Let's get up our formula sheet here. So sort of stuff I might want to find then is maybe the shear stress. Obviously I would want to know for something like that I need to know the polar second moment of area. I might want to know the maximum well, probably I'd want to know maybe the largest compressive stress there, maybe the stress components. What else? I could apply some failure criteria to this problem, so I could do that. Got a factor of safety, and maybe if it's a rod or shaft, there's two ways that things could break, and I might be interested in examining what the maximum shear stress is compared with the maximum in magnitude compressive tensile stress. If something breaks orthogonal, it's kind of brittle, then it will tend to break due to the compressive stress. Whereas if something's a bit more ductile, maybe it's warm or whatever. If it's a drill going round, it might break due to shear stress, so it might sort of shear in at an angle there. So these are the sort of things I might want to examine. Let's take them in turn. So what's the most obvious thing we could establish? Well, that's the compressive stress. So let's look at that. Let's start there. So compressive stress, I will call this the stress going off in this direction. Although I probably don't want to do that. I want to define such that it's going to be a negative. So I will make my x point outwards. And right hand rule, yeah. So first finger can be my x, my y can be sort of like going off in that direction, and then the z will be coming out. So it will be coming out in the radial sense. So that would be like your y sort of thing. Right, so that gives me a negative. So got a minus p over the area. So I want to put that in. So we're going to have minus 220,000 over the area using this 50. So we'll have pi 50 times 10 to the minus 3 to the power 3 divided by 4. So we'll put the 4 on top. So that what do we get for that? 220,123 times by 4. Yeah, so I'm using pi d squared divided by 4, not pi r squared. Yep, divide that by the pi, divide that by 50 minus 3 to the power 2. So we get a decent amount of compressive stress there. So 1, 1, 2, I use 5 sig fig megapascals. So that's the compressive stress. La France appelle. What about the shear stress, which will be caused from the torsion? How are we going to find that? To look at that one, we'll use the engineer's torsion equation. So the first two columns, and we're going to have this expression here. So this is my shear stress here. So let's rearrange this. It will be the torque divided by the polar second motive area times by the radius. And then we can look up, because on the formula sheet here, we've been given things in terms of R, so we use radius this time. Well, I tend not to. So let's substitute that in, and we're going to get the torque on little r divided by pi r to the 4 over 2. So watch out, that's the polar version, i.e. the J, not the I, which would be the if you was bending it, not twisting it. So one of the r's is going to cancel here, so that's going to give us 2 torque divided by pi r to the power 3. So we're ready to put the numbers in. So 2 times 650 divided by pi divided by, okay, I'm using radius here, so 25, don't make a mistake there, to the power of 3. And we're going to get a shear stress of 23,483 megapascals. And that's the shear stress in the XY plane. Right, so one of them is trying to pull it in this direction, or actually the other way around, this direction, and this one will be trying to pull it in this direction. We thought about an element. Okay, so I've worked out what the stress is in that x direction. I worked out the shear is in that direction. What kind of things would I want to know? These are in terms of structure, these are the two equations of greatest interest, really, isn't it? So we've got what's the maximum amount of stress in a tensile sense, and what's the maximum amount of stress in a shear stress sense. You notice that the shear stress equation is tied up in here, so it makes sense to work out your maximum shear stress first. So maximum shear stress equals right, so in terms of this plane, it would be actually coming out, so it would be the Z direction here, so not Y really. Well, the formula uses y, so I'll carry on using y. Actually, I'm talking rubbish. Okay, so you've got to remember that there's a difference between this shearing action and am I trying to push it off into the y direction? And I'm not. I'm just trying to squash it. So there's no bending or any kind of motion like that in here. So the stress in the y direction is 0. Yeah, so this is my compressive stress here, and the sort of like straight stress that I'm trying to, if I was trying to push it off in that orthogonal direction, is 0 as well. So that is going to have a 0 value. So we want the 1, 1, 2. It's a plane stress problem we're dealing with, and I've forgotten to square it. 2 square plus 26.483 square. So let's work that out. Plus 26.483 squared. And I'll take the square root. And I've gone wrong. 112.05 divided by 2. Square it. Plus 26.438 square it. Square root. Okay, so that's plausible. $61.969 megapascals. Right, so the next thing is I might want to find what the stress is, the maximum stress in this particular XY plane. So imagine that we're just on this surface here and we want to find out where on that particular little square on the top, on the outer part of the shaft, where can I point my stress to get the maximum amount of possible stress on that particular plane? So that's going to be our principal stress. It's actually going to be the most negative one that we're interested in here, isn't it? So we go back to this max and min. And what we find is that if you can point the location of maximum stress, the orthogonal in that particular plane will be the minimum, or rather in this case the maximum, because it'll be a positive value. But the point is that those two things are orthogonal. That's the important point. So here we're going to use stress X, stress Y, 2, and you notice that becomes plus or minus shear stress max. So take the 112.05, divide that by 2, and that gives us minus 56 plus or minus 61.969. So our maximum will be 61.969, take away 56, 0.025. So the maximum positive stress will be 5.944 megapascals. And the other one will be, actually, have I got that right? Yeah, minus that plus, yeah. And that will be a negative. So minus 117.994 megapascals. In terms of structure, it depends what kind of shaft I'm looking at. I might be dealing with a shaft which has an awful lot of uh, the if you looked at the stress strain plot, it might have very different behavior when you're trying to pull it and when you're trying to compress it. So it's very unlikely, to be honest. But in this particular case, we might be more worried about the 5.94 because it's a positive tensile stress than the minus 100 and almost 18 negative stress. But those are the two things that you would want to compare, and then you want to compare it against your experiments of when you try to pull it apart or squash it. So, and that would be the other stress value that you'd be interested in. If you think that it might fracture in a kind of ductile sense. What other things we could do? These values actually structural engineers tend not to tend not to look at maximum stresses or shear stresses. They tend to use almost always von Mises stresses. So the von Mises stresses, we've got a formula for that for a plane case, and that is stress 1 squared, stress 2 squared, minus stress 1, stress 2. And that's an equation that's valid for a plane stress case. So again, when we're on a surface of something usually, and we've only got two stress components. So we've got two stress components. So notice here, I've got two stress components. Now the requirement for me to be able to use this particular equation is that I have no shear stress. And if I'm orientating my stress along the maximum and the min stress orientations, that will be the case where we have no shear stress. So this max and min for me will be the equivalent of stress 1 and stress 2. So we put these two numbers in here. Stress 1 is 5, so stress is the most positive here. I can ignore the minus sign. Here we're going to have minus minus, so be careful, so that becomes a plus. And we're going to take the square root of that. So we have 5.944 squared plus 117.994 squared plus 5.944 times by 117.994. Then we take the square root of that. So that would tell me, if I was analyzing this thing and I was trying to pull it apart, doing a standard tensile test, that I would need to keep I'd be interested in finding out what the yield stress is probably, and is it less than the 121 megapascals from my experiments. But because I'm doing a factor of safety 2, my von Mises stress is actually going to be the maximum stress I can apply. So your maximum stress that you can apply will be whatever you find the von Mises stress to be. So that's the 1, and we divide it by 2. So we make sure that the maximum stress that we're going to apply will be less than that. So let's divide that by 2. And then that gives us 60.5 megapascals. Right, so this is something that a lot of people find quite confusing. I've found previously that the maximum stress and the minimum stress, unfortunately, is a compressive case, so it's not such a kind of like really confusing thing. It'd be nicer if it's a positive number. But let's imagine we were looking at a case where we weren't compressing it, but we were pulling it apart. And we ended up with that the maximum stress was this 118. And then you work out the von Mises stresses. They always give you a positive number here. And then you find that the maximum stress according to von Mises criteria is 121. What do you notice? You notice that the von Mises stress criteria is telling you you can pull it apart a little bit more than if you were just having a completely uniaxial case. So if we had no twisting here, the twisting actually is what it's causing is going to be a higher load than you'd think that would be applicable. So you know, if you come back up to this value here, this 112, you notice that is actually going to be less than this particular case here. So the von Mises stress criteria is actually telling you that you can go a little bit beyond what you'd think that you would be just applying if you're just doing a simple uniaxial load. So that kind of blows a lot of students' mind. You're actually getting a number higher than your simple stress max for it to be safe. But of course, we're going to apply a factor of safety, so that brings us the 1-to-1 down. That brings that 1-to-1 down. So that's good news. Okay, so you know, played around structurally. Hopefully, that will be of interest to you.